Jeff Street's going to continue telling us about the Ricci flow.
So yeah, thanks for that introduction, and thanks again for letting me speak. So yeah, so like I said yesterday, so yesterday was sort of generalized Ricci flow in total, and then today the complex structures will show up. So yeah, I hope you'll feel as free to ask questions today as yesterday. It was a lot of fun yesterday. So yeah, so the starting point. Oh no, it stopped working. Yeah, click should be all it takes, I think. Yeah, okay. Yeah. So the starting point is the nice, by now very old observation that complex Kähler geometry has a nice interaction with the classic Ricci flow equation and gets called Kähler-Ricci flow. So the sort of most rudimentary points of this, so we say a one parameter family, so a complex manifold MJ and with a one parameter family of metrics solves Kähler-Ricci flow if and only if the metrics are just evolving by the Ricci flow equation here, which is the same as the Kähler forms omega evolving by minus rho. So rho is the Ricci form. The Ricci tensor paired with J, factor of 1/2. So some very basic points of Kähler-Ricci flow. So for one thing, there's this evolution of the Kähler class. So a Kähler metric comes equipped with a Kähler class, and it moves in the direction of minus the first term class. Another sort of very basic point of the theory is that sort of up to this finite dimensional sort of ambiguity of moving in the Kähler class, the PDE reduces to a flow of a Kähler potential, which is this like parabolic complex motion pair equation. So, and this is because it sort of reduces to a scalar, this is what lets you get, you know, much farther with Kähler-Ricci flow than regular Ricci flow. So much stronger results in general. So yeah, so the point of this talk is that you can extend aspects of this story to more general complex manifolds beyond Kähler using generalized Ricci flows. Okay. So just to dive in, I'll sort of take what seems to be a detour and then sort of plug back into generalized Ricci flow. So we have this basic definition. So we have a Hermitian manifold. So J is integrable, G is compatible with J. We call it pluriclosed if so omega is the Kähler form. We define H to be DC omega like this, and then we just ask that H is closed. Okay. So I think this definition is quite familiar to most of us.
So Jeff, I have just a stupid question.
Yeah.
So why on the right-hand side equation there's no factor 2? So I thought that the Kähler form is just obtained by plugging in J into the metric, and the form
it's because my convention for rho includes a factor of 1/2.
So you have redefined it such a.
Sorry, yeah, I guess by my convention it's not just Ricci paired with J. It's basically it sort of shows up because of the Bianchi identity. You're taking like the endomorphism trace and blah blah. Yeah.
Can I ask this silly question? Yeah. What does the name come from?
Pluriclosed. I forget where I first learned it. I forget the paper where I first learned this name, but I must say I prefer it 1,000 times to SKT. Sorry, just as a terminology. I could give you an hour-long talk on that later.
Pluriharmonic.
Yeah, it's like plurisubharmonic, pluriharmonic. I mean, yeah, it's pluriharmonic maybe would have been a better term, but pluriclosed, it's pretty old, I think.
Yeah, pluriharmonic just means harmonic in multiple dimensions, and this is 2 dimensions.
Yeah. Yeah. Okay, so so I want to define now this pluriclosed flow, sort of in the following way. So for pluriclosed metrics, we have this Bismuth connection, a Nabla plus. So this is the same Nabla plus from the previous talk, and the key point is that it's in fact a Hermitian connection. Okay. With H as defined in the previous slide. So I let omega denote the curvature of this, and now I define this rho B. So here's, by the way, this 1/2 that I'm talking about. So rho B is the Bismuth-Ricci form. So I'm taking the like endomorphism trace of omega composed of J, okay, with a factor of 1/2. So this represents up to some multiple, the first term class. It's closed, but but in general, it's not type 1/1. Okay, it's sort of an important point. So we can just write this down, write down the pluriclosed flow in a very kind of ad hoc way. And this is, of course, how we first sort of understood it. In fact, not even like this. It was even more sort of ad hoc than this. But so we can just evolve the pluriclosed Kähler form by minus rho B 1/1. Right. So I do have to project onto 1, 1 to preserve compatibility. And then basically, because rho B is closed, it will follow that pluriclosed is preserved by this. Okay. So the 1, 1 part is pluriclosed. So yeah, this we could take to be the definition of the PDE, but I immediately want to sort of connect it back to generalized Ricci flow. That's the whole point. So I need one more definition. So for a pluriclosed metric, I define this Lie form theta d star omega composed of J. So this is some further kind of measure of the non-Kählerness, but it's a one form. It's kind of part of the torsion, if you like. And then so this old theorem of myself and Tian says the following. So if I take a solution of pluriclosed flow as defined here, then it has some family of Riemannian metrics and closed 3 forms attached to it. Then they solve the following PDE. So dg dt is minus twice Ricci plus 1/2 h squared, but then minus the Lie derivative with respect to the Lie vector field. So you raise an index on the Lie vector field. And then the 3 form is evolving by the Hodge-Laplacian minus, again, a Lie derivative term. And so, yeah, so I guess I wrote it here in terms of H instead of in terms of B, but you can equivalently write it in terms of B. And then, of course, what you see, the whole point is that this is a generalized Ricci flow except for this gauge term, right? And this is actually quite an important point for later, okay? So, yeah, so the upshot is you can think of it, we can kind of turn the whole story on its head and say, actually, the generalized Ricci flow preserves pluriclosed, kind of, because only after a non-trivial flow of J. So like in the Kähler world, you just say Ricci flow preserves Kähler, period. Right? So if it starts Kähler, then it stays Kähler with respect to the same complex structure, but that's not quite true with the generalized Ricci flow, right? I have to flow the J because I need to, if I want to, let me just go back. If I want to like remove this gauge ambiguity, I have to pull everything back, including J, right? Okay, so yeah, here it is. Yeah, so I pull everything back by J and then, yeah, so dj dt is L theta sharp J. So again, in the spirit of sort of asking questions for this audience that maybe the generalized world has something to say about. So I've always wondered if this evolution for J, I mean, it comes from my point of view, and it's just a sort of a very ad hoc way. It's just kind of there in these natural equations, and you work with it, blah blah. But I just wonder if it can be derived from first principles in some way, like for instance from this F functional. Like if you think of the F functional restricted to very close or something like this. But I don't know. I don't know a nice derivation. Yeah, and then again, I just want to sort of reference back to this question about sort of the relationship to holonomial. So here, clearly, what it's showing is that this generalized Ricci flow, well, it preserves, well, again, once augmented with this PDE of J, it preserves compatibility with J, and so it's preserving this holonomial reduction for the Bismuth connection. Okay. So I wonder if there's more.
Can I just ask one question to follow up on this? Because right now we have two things: you have the holonomial reduction and integrability of J, which is not like, because you have torsion, it does not follow from just holonomial reduction. So it's like it's an extra hypothesis.
Sorry, what? I don't
like
quite
right now, because you're doing pluriclosed, so you have an integrable complex structure and the holonomial reduction for the Bismuth connection. But if you just had the Bismuth, the holonomial reduction, you would not have that the complex structure has to be integrable.
Yeah, right.
So what if J was not integrable? Like, to the check in that case,
I don't think I could say much if J was not integrable.
Because that would be like the first thing to check. Because of course, in the original case, all the special holonomial manifolds are fixed points except for the Kähler one. So it kind of feels like it could be an accident, right?
I see.
So it would be worth checking for the case when J is not integrable if the holonomial is also preserved.
Okay, yeah, I see what you mean. Yeah, that's interesting. Okay, yeah. And also, I want to point out that in this for this pluriclosed flow, the torsion H has like a holomorphic potential. So in generalized Ricci flow, H is H naught plus dB, but now we have a potential for like the 2-1 piece of the torsion. Okay, so you get a sort of some extra structure here. So if we let beta be a time-dependent family of 2-0 forms that solves this PDE, so right, we kind of arbitrarily chopped off the 2-0 part when we define pluriclosed flow. And of course, in this setting, everything is determined by omega. So it's kind of like, well, that gave you everything, but clearly you kind of missed something with this 2-0 part. And so it makes sense to include this as part of the equation. So d beta dt is sort of recovering this 2-0 part of the flow. And then it's just a trivial fact of chasing through the definitions that the time-dependent torsion, that the 2-1 piece will be the initial one minus I d bar beta. Okay, just if you have a holomorphic potential for the torsion now.
Sir, what do you mean by holomorphic? Like it's written there that it's not.
This is what I mean by a holomorphic potential. So like up to a background term, it's d bar beta. The moving torsion is d bar beta.
Like, is this holomorphic in any way? No, because it's 2, 0.
I mean, it's like solving the d bar equation. D bar beta is not 0; it's equal to the torsion. Does it make sense?
Yeah.
Oh, yeah. Okay. Yeah. Yeah. Okay. And so, yeah. So I'm gonna sort of overlap with Josh's talk from yesterday. So maybe I go a little bit quickly. So recently we were able to give this reformulation of pluriclosed flow using holomorphic Courant algebroids, following some really nice work of Bismuth. So I just want to quickly describe this. So if we have a pluriclosed metric omega naught, we can define this bundle Q, which is the T10 plus lambda 10. But we endow it with this twisted d bar operator. Okay, so d bar is now twisted by omega naught in the following way. So it acts by x plus xi by the usual d bar operator, but then plus this extra term. So I, the interior product of x with del omega naught. And then of course the integrability of this operator is precisely the pluriclosed condition, right? That's easy to check. So now if I have some other pluriclosed metric, so I think of del omega naught as kind of part of the background. So if I have some other pluriclosed metric, and then I have to impose this topological condition, right? So the 2-1 Dolbeault torsion classes have to be the same. So I can solve this equation for a potential. Then I can define a metric on Q. Okay, this is this capital G. So this formula probably looks a bit nutty, but it should sort of remind you of maybe the first slide from yesterday. I mean, this is, maybe in this crowd it's quite familiar, but this is basically the beta transform of this standard off-diagonal metric. Which in this case is Hermitian. And what's really nice in this setting, right? So I sort of said a few words yesterday about this theory of connections and curvature in the sort of real generalized geometry setting. And well, there's a lot of hedging about it, but of course here there's no hedging at all. It's a holomorphic bundle with a Hermitian metric. It has a Chern connection, right? So it's a very straightforward thing. So if I take the Chern connection, I can then produce what I'll call this Hermitian-Yang-Mills curvature tensor SG. So that's just the two-form trace of the curvature of the Chern curvature. Okay, I call it S upper G, but of course I'm taking the trace with respect to little g. Right, so it's whereas usually in Hermitian-Yang-Mills theory, the metric on the base is part of the background, but here, of course, it's all in play. Everything is determined using little g, right? My metric on the base space and my metric on the bundle Q. All right, and then so the sort of amazing fact, it's even sort of more amazing than this. Basically, the amazing fact which Josh discussed is basically that the Chern connection of G is sort of canonically identified using this graph map with the Bismuth connection downstairs. And in particular, the curvatures are then identified in a certain way. It's a fairly complicated map, but the curvatures are identified in such a way. So this S vanishes precisely. I mean, I wrote it this way, but it's precisely if rho B vanishes. I just wrote rho B in terms of its symmetric and skew symmetric part. Or it's 1-1 and 2-0 parts. Okay. So it's like precisely equivalent to rho B, this tensor S, okay? So to me, it's kind of like a mind-blowing thing. And so furthermore, if omega t is a solution of pluriclosed flow, there should also be a beta t here. That's the whole point. If I have omega t and then also this time-dependent beta t, then I can define capital G sub t, and then the pluriclosed flow is expressed looking a lot like this Hermitian-Yang-Mills flow. Okay, but again, it's really important to remember that this is not Hermitian-Yang-Mills flow because the trace is with respect to the moving metric. Okay, so I just sort of summarize in this line what was happening on the previous slide. So but nonetheless, using this observation, you can apply these Mumford-Takimoto slope stability obstructions to still to produce obstructions to the existence of rho B equals 0. So these will be fixed points for the pluriclosed flow, right? So a theme throughout the talk I'll sort of come back to is sort of pointing towards like some version of like Yau's theorem for generalized Kähler structures, pluriclosed structures, okay? And so most naively, you want to solve for rho b equals 0. Okay. Point is there's obstructions. And so this is a theorem we proved last year. So roughly speaking, in every dimension, we construct infinitely many pluriclosed manifolds with vanishing first Chern class, which do not admit a solution to rho b equals 0. Okay. So it's a highly obstructed problem. In dimension 4, it was it's basically already known by a theorem I'll mention soon. But now we produce these examples in every dimension. And it's just to show that, well, the most naive version of a Yau conjecture is wildly wrong. Okay, so C10 is not even close to enough in this set. Okay. Again, some general questions. Can this be extended to yield obstructions to the existence of solitons? So I haven't really properly defined solitons. I mean, we defined them last time, and all it really means is the soliton PDE from last time, plus it's also pluriclosed. So maybe there are obstructions to solitons as well. And then again, just as a kind of general remark, it's something that amazes me after reading this paper. I just wonder how Bismuth found this in the first place in 1989. I mean, it's like, it's all really generalized geometry. And this observation that we use and sort of recast using holomorphic current algebroids is a tossed off remark at the end of the paper. I mean, maybe it's how he discovered it all in the first place. This is his paper in non-Kähler index theorem. I mean, it's kind of amazing. Just sort of, oh, by the way, there's this other complex structure. And it's really amazing. And I just wonder if somehow that whole work has a generalized flavor. I mean, I have no idea, but it probably really somehow belongs in this context. So anyways, I just thought I would mention that. Yeah, so again, yeah, pointing towards the guessing at what a Yau theorem could be in these settings. I want to mention this old result of Godeshan-Ivanov. So a lot of the talk will be restricted to complex surfaces. So the Godeshan-Ivanov classify all possible compact complex surfaces which have a pluriclosed metric, which is Bismuth-Ricci flat. And the answer is pretty simple. Either H is 0 and is Calabi-Yau, or there's really just one very rigid class of examples, and this is it. So it's what's called a standard Hopf surface. So I have the definition of Hopf surface, I think like 4 times in this talk, but anyways. So it's C2 minus the origin, and you mod out by some dilation, where what's special about it is that the magnitude of the two factors is equal. Okay, it's called standard Hopf surface. This is like the most rigid class of Hopf surfaces. And the metric is the round metric, direct sum standard metric on S1, and then H is a volume form. So you can see this is really like a biinvariant metric. It's the biinvariant metric on S3 I discussed yesterday, plus an extra flat S1 factor, okay? So it's in fact Bismuth flat. So it's kind of surprising, right? The only like non-Kähler sort of Ricci flat example is already just flat. Okay. And yeah, I just, sort of some remarks just to kind of set the stage. Just mention that a lot of other non-Kähler complex surfaces arise as elliptic vibrations. So when the quadratic dimension is 1, they're all elliptic vibrations and only multiple fibers occur. You can cover the manifold. There's a finite cover, which is a genuine principal T2 bundle over a Riemann surface, in this case of negative Euler characteristic. And when the quadratic dimension is 0, it's exactly the same story, but the base space now has Euler characteristic 0. And then, of course, even these Hopf surfaces, these standard Hopf surfaces are in fact also principal T2 bundles over S2. So in fact, this result from last time I discussed about these like invariant generalized Ricci flows on S3, in fact, are describing pluriclosed flow lines on, I didn't really discuss this case 1 and 2 yesterday, but yeah, it's saying something about pluriclosed flows on those manifolds. Okay, but so I want to now state a theorem with some global existence results on these manifolds. So so if M4J is a compact complex non-Kähler surface of non-negative quadratic dimension, then we show the flow is global with arbitrary initial data. Okay, so it has global existence. And conjecturally, what's happening is you will not get convergence. So we know these things cannot converge to rho b equals 0, right? Because they don't exist. That's from this earlier theorem. But basically what's happening is you should take a blowdown limit and you will converge either to a point in the case of quadratic dimension 0, or you're converged to the negative Euler characteristic Riemann surface in the case that kappa is 1. And that, in fact, we can prove if the initial data is T2 invariant. Okay, that's part of what I discussed yesterday. Then second part is if we take a standard Hopf surface, then if we have an arbitrary pluriclosed metric, then the pluriclosed flow is again global, and this time converges to this flat structure, okay, this Bismuth flat structure. Because again, this is like a special case of what Josh talked about yesterday. And the statement is stronger now, more or less because of this Godeshan-Ivanov result, because we know very rigidly like the uniqueness in that set.
So in the first case, even if the Kodaira dimension is 0, which I guess would be like the Kodaira manifold, is that
Yeah.
right?
Then the blowdown limit is a point. It converges to a point. Yeah. You can take sort of, because you know already like what's going on, you can take different blowdown limits and like you could converge to the torus if you like.
Yeah.
But it takes a very delicate rescaling. It's not like the standard rescaling.
I thought in the symplectic curvature flow it converges to the base, like the Kodaira manifold, like the T2 fibers shrink and the base expands, and so then when you take the limit, you sort of get T2.
That could be true. I don't remember offhand. But of course it's a different PDE, so.
Yeah, no, but it's just different. It
But
behaves
yeah,
differently.
okay. Yeah. And so, yeah, I just want to say a few words about the proof and what's going, well, the proof of the second item. I won't say anything about the proof of the first item. So yeah, Josh discussed that a bit yesterday. So I'll say a little G Hopf is this Hopf metric on the previous slide, this flat one. And then we use this by this discussion of this Bismuth construction to construct a Hermitian metric on Q. And the point is, you can get some sort of very favorable PDE. So the typical situation for these equations when you apply like Schwartz lemma to try to estimate, say, the metric in some C0 sense is you get some like heat operator and it will produce some reaction term which is nonlinear. But the reaction term always involves sort of the curvature of your reference metric. Okay, so the point is this Chi Hopf is Bismuth flat. And by this Bismuth identification, it means that this capital G is Chern flat, okay? And so what happens is you apply the heat operator to this trace, you just get 0. What would normally be on the right-hand side is something nonlinear, okay? Which sort of, you know, you can't do a whole lot with it in just in that form. But because of this very special structure, it's just 0. So this immediately just tells you that the metric is controlled in this like sort of L infinity sense, like the eigenvalues of the metric aren't going to 0 or infinity. Okay. And then you can go a little bit further. So if I let epsilon denote the difference of the Chern connection, so I have this kind of background Chern connection of the Hopf metric, and then I have my time-dependent one, and I can apply the heat operator to the magnitude of the connection squared. And here I have to use the base metric and the bundle metric. And again, it's just sort of magically non-positive. And normally on the right-hand side, there'd be sort of this mess of terms involving the Chern curvature of the reference metric. But those are all gone because of the because this G Hopf is Chern flat. Okay. And this is, in some sense, this is like an extension of like Yao's C3 estimate to the setting of pluriclosed flow. I mean, even in this more general, even without a flat background with some kind of background terms on the right-hand side, it's still a natural extension of this C3 estimate to the setting of pluriclosed flow. Okay. So this is a key part of the Calabi-Yau. Okay. Yeah, no, maybe I pause. Maybe I'm going too fast. Because I'm going to sort of switch gears after this to generalized Caleb. Okay. Anyways, so yeah, so that's all I guess I'll say about pluriclosed flow per se. But so now I'll talk about this generalized Caylor-Ricci flow. So to start, I'll recall the lowest tech version. So this original Gates-Holorowczyk version of generalized Caylor geometry. So the 2n-dimensional manifold with a metric, 2 integrable complex structures, which for me are I and J. And then you have this integrability condition, which Marco wrote down. So dci omega I, we call that H. That should be minus dcj omega J. And then H should, of course, be closed. And most naively, it's sort of just pluriclosed in 2 ways. It's one metric, which is sort of pluriclosed in 2 ways, in the most naive sense. So sort of immediately, it's essentially immediate that you can then write down what should be the generalized Caylor-Ricci flow, right? Because if I didn't know anything about J, I mean, this would just be pluriclosed flow, right? But then also, if I didn't know anything about I, the other one would also be pluriclose flow. But it turns out it all sort of fits together nicely. And indeed, this system of PDEs preserves these integrability conditions. Okay. So the point is, we just have two of these like gauge terms now. Both I and J are flowing by gauged. Okay.
Even though the H changes by a sign when you compare I and J.
Yes, but it all works out. Yeah. Basically, because the key point really is that the symmetric part of the Bismuth-Ricci tensor is invariant under that sign change. So the metric does not see the difference in the sign. That's essentially why, because it's just H squared, right? It's a very dumb reason, but somehow that's that's why it works, I guess. Or I guess I should say a very low-tech reason. I'm sure there's a more high-minded explanation for why it works. And notice, and again, this is sort of an important point. If I want to, so for pluriclose flow, it's no problem. We can work on a fixed complex manifold if you like, but you simply cannot fix them both. You can't fix both I and J, and this is a really important part of the story. So if I like, I can pull back by the diffeomorphisms generated by theta I, and I can fix I or J, but not both. Okay. And again, I have to point to this question. So in some sense, is this like a holonomic preservation? I don't know. Well, it would be interesting. So yeah, I want to very briefly.
Sorry, about this holonomic preservation. So we know that T plus T star has holonomy UN cross UN for the generalized connection that exists on it, right?
What's so for a generalized connection?
Yeah, for the standard one, the one that's the sum of the two Bismuth connections.
Yeah, okay. Yeah.
One on V plus and one on V minus.
Yeah.
So is your question whether the GK Ricci flow preserves that holonomy? What's the question really?
Well, I don't exactly know what the question is. That's the problem.
But this is like the naive holonomy, but how do you define holonomy for a generalized connection or a generalized metric? And I mean, it's always going to be contained in UN cross UN, but it could be smaller. And then how do you control whether it keeps being smaller for OT or not?
Okay.
So yeah, I want to say a little bit about sort of recasting this in the generalized language. So I kind of gave the kind of by hands definition of the flow, but so what does it look like in the generalized language? So again, yeah, so as Marco of course already discussed, so a generalized complex structure is a complex structure on a Courant's algebroid whose I eigenbundle is Courant's integrable. And then a generalized Kähler structure, again, Marco just discussed this, is a pair of such GC structures which commute and which whose product minus the product gives a generalized metric. Okay. So with a student, Matt Gibson, a couple of years ago, we wrote down what this PDE looks like in terms of J1 and J2. So if I take a solution to this GKRF in this I fixed gauge, so again, I move it in a specific way to prefer I, then you can write down the PDEs for J1 and J2, and this is what they look like. So here, sorry, yeah, this row I, that's the Bismuth row for the MI manifold. Sorry, the notation's slightly different. Maybe row BI is maybe better, but also worse. Yeah, so in any case, I just write this down to indicate that indeed we can sort of express these in a clean way. And I found myself wondering in Marco's talk, so this is something I thought about before, but not very seriously. So, so we have this picture of pluriclose flow in terms of holomorphic Courant algebroids. We at least now can express this generalized Kähler-Ricci flow in terms of these generalized complex structures. Almost certainly, I guess if you do this Courant reduction, as he described, to produce these two holomorphic Courant algebroids, I mean, almost certainly this is reproducing two versions of this Bismuth picture. Again, up to sort of a gauge transformation, depending on how you set it up. I don't know if there's any hay to be made with that analytically, but I would imagine that must be true. It's kind of interesting. Okay, yeah, so what can we say about this, the generalized Kähler-Ricci flow? So associated to a GK structure is a real Poisson tensor discovered by Hitchin. So I call this sigma, which I hope is okay. So this 1/2 a G inverse, the commutator of I and J. This thing is a pretty magical object. So it's type 2002 with respect to both I and J. So it's, yeah. And so it's also holomorphic in both senses. So the I20 part is I holomorphic and the J20 part is J holomorphic. Okay. And a basic fact of the theory is that this pulse line tensor is preserved by the flow. Again, if I put it in the I fixed gauge. So if I flow this I fixed gauge, the sigma is fixed. So it really is part of the background of the equation. Okay.
And if not, it moves in some simple way. If you don't do the I fixed gauge.
Well, it's being pulled back by whatever gauge you put it in there, I suppose. Yeah. So yeah, and this sigma has a lot to say about what the equation looks like. So the sort of closest to Kähler is when sigma is 0. And of course, then it follows that I and J commute. And because of this, you get a splitting of the I holomorphic tangent bundle into pieces T plus and minus. Yeah, in this subject, you always have to be careful with plus and minus. This has nothing to do with any plus minus that Marco wrote down. I don't think. Again, I just write this to make some contact with the sort of theory of generalized Kähler-Ricci flow. So locally, you can reduce this PDE to a scalar PDE for a potential. And it looks like what I call this kind of twisted Monge-Ampere equation. So the standard complex Monge-Ampere, parabolic complex Monge-Ampere would just be something like df dt, this log determinant d bar f. And somehow just ignoring background terms, this is sort of the local picture of Kähler-Ricci flow. But now we get this funny mixture of terms. So I get the log of some determinant ratio so it's the determinant of the Hessian of f on the plus part divided by the determinant of minus the Hessian on the minus part. And the point is this potential is not convex. It's convex concave. So it's convex in the plus it's pluri-subharmonic in the plus directions and it's pluri-superharmonic in the minus directions. Okay. And this is really a key feature of this PDE. So like an essential feature of a vast majority of literature on fully nonlinear equations is some kind of convexity hypothesis. There's almost nothing about PDEs that are not convex. This one is not. so that's why there's some new challenges and why even this Yao C3 thing is a sort of a very non-trivial thing because you can't apply these sort of Evans-Krylov type methods to this equation. Okay, the complete opposite, the most generalized of generalized Kähler is the case maybe when sigma is invertible. Okay, so this is even more special than symplectic type, which Marco was always talking about. This is really like where both generalized complex structures are symplectic type. Okay, so in this case, the structure is actually determined algebraically. I've determined twice. Yeah, so it's determined algebraically by sigma and j. These completely actually give you the whole structure. I mean, and I is always there as part of the background. And you can express that, this is what I mean when I say that this gauge thing is really an essential part of the flow. Like it's really governing the entire PDE in this setting, okay? So dj dt is Lxj, where x is a Hamiltonian vector field or a Poisson vector field. So sigma d phi, where phi again has this kind of, this kind of non-convex structure. So phi is log of determinant I plus j divided by determinant I minus j. So the non-degeneracy hypothesis is precisely that both of those matrices endomorphisms are invertible. Okay. And so, yeah, maybe I just say in words, this is, I guess, what Marco calls the Hamiltonian flow construction, or maybe like a special case, because the sigma is fixed. But this is precisely what it means to be a Hamiltonian flow. And it's driven by this special function, which is, I use this phi in all settings, it will come up again, is this Bismuth Ricci potential. And so for later, maybe I just mention, so if I have this like if J1 is determined by a closed pure spinner, so if both of these are determined by some closed pure spinners, then this phi is precisely this up to taking a log, this like Calabi-Yau quantity defined by Marco. And the kind of magical point underlying a lot of the analysis and underlying what's going on here is that like rho bi is dj d phi. The ij is not a typo. That's a mysterious part of the story. And of course, like we know this rho bi is not type 1 with respect to I. Somehow it fits with that. Of course, and yeah, but again, this formula should look very recognizable. So if you're familiar at all with this sort of language, like you can see the Kähler case inside this. So the Kähler case, let's just say Calabi-Yau. One of the J's is J omega. The other J is determined by a holomorphic volume form. This is precisely then the Calabi-Yau ratio. This is omega to the n divided by the, too many omegas, but the volume form wedge its conjugate. And then in fact, then it's just rho is d, then I equals j, and rho is did of that ratio, right? So this is some generalization of this basic like transgression formula in Kähler geometry. Okay. So yeah, so the sort of general broad takeaway that sort of generalizes the statement that that sort of unifies all these cases is that generalized Kähler Ricci flow is the flow construction driven by the Bismuth Ricci potential in all these cases. Okay. Okay. So I want to state now a consequence for generalized Kähler geometry that comes out of this earlier result. So fairly well-known thing in this subject is that this Bismuth flat structure on the standard Hopf surface that I discussed earlier is in fact generalized Kähler in two very different ways. So again, here's this definition of this standard Hopf surface, and here I write down the Hopf metric. This is explicitly what it looks like on C2. We look to C2. So on the one hand, on C2, you can just change the orientation of one of the complex planes. That gives a new complex structure, which is obviously still compatible with this metric. That's easy to see. And this is a commuting type structure, right? So here the Poisson tensor will be 0. On the other hand, you can construct J by this very beautiful kind of geometric idea, which I think is due to Marco. So you pull back J through an orientation preserving inversion in the unit sphere. And you can show that commutes with the Z action on C2. And then you produce this second complex structure. And this one is generically non-degenerate. So the Poisson tensor is this standard Poisson tensor on C2, Z1, Z2, del Z1, which del Z2. But of course, it has a degeneracy locus, right? So the picture of the fundamental domain is you have this picture of C2, and then you have this fundamental domain, and then of course sigma, like here, I equals J, and here I equals minus J. So you have these two elliptic curves, which are where the Poisson tensor degenerates, but it's invertible everywhere else. Okay, so a corollary of this theorem that I mentioned earlier. So I stated this theorem for pluriclose flow. So you fix one of the complex structures, the flow exists globally, it converges to this flat structure. Great. But of course, a generalized Kähler Ricci flow is just pluriclose flow in two ways. So what it's telling you is you can start with really any generalized Kähler structure with a fixed Poisson tensor. I mean, we think of that as part of the background. And they will all be deformable to the standard one, to this standard structure. Okay. And there's really only sort of two choices for sigma up to scale. It's just these two choices, either the standard one or 0. That's it. Those are your only two choices. But so for any sigma, they're all deformable. So I mean, yeah, to make some connection with Marco's talk. So you gave this description of how we should think geometrically about the sort of like generalized Kähler class. But in this way, I'm thinking just very naively. I mean, I just have some space of tensors, and they're all deformable through generalized Kähler structures to this standard one. So the topology of this space is trivial.
Could you say, in your opinion, this kind of amazing result? So what is this analog of in the Kähler case?
Right. So the analogs in the Kähler case are probably not so impressive, right? I mean, the Kähler cone is obviously contractible. I mean, it has a linear, it's a cone in a linear space. It's obviously contractible. So there's not really, a non-trivial analog in that setting. But here, with this very nonlinear description of how you even move through this space, I mean, in other settings, not quite in this setting, but so for instance, I'll mention a similar result like on the torus. You're really talking about like a space of like Hamiltonian diffeomorphisms of a holomorphic symplectic form.
But do you view this as an analog of an extremal Kähler metric? Or what is
the metric, this Hopf metric, of course, yeah, is like Calabi-Yau. It's generalized Calabi-Yau in some sense, non-Kähler Calabi-Yau.
But GC structures don't have a pure spinner, right?
No, yes, okay, yeah, we're jumping ahead to the end, but not okay. So for me, most naively, Calabi-Yau should just be one of these pluriclosed or GK structures which satisfies a certain Ricci flat condition, like rho b equals 0, for instance. Okay. And so from that point of view, definitely this thing is Calabi-Yau for me, right?
Let me point of view as well, right?
Yeah, exactly. But so what you just mentioned is a key difficulty in really understanding what should the Calabi-Yau conjecture be in GK geometry. Yeah, it's like I think it's a very subtle point. Yeah. And I mean, and again, yeah. So, as part of the story, like this theorem of Godeshan-Ivanov that I mentioned sort of close to the beginning, is kind of a version of Calabi-Yau, if you like, for complex surfaces. It's telling you exactly what they are. It's not sort of derived in a priori way. It's not saying, give me a complex manifold with XYZ conditions. I can produce for you a Bismuth-Ricci flat manifold, but it is nonetheless a classification, right? It is a complete description of all possible solutions.
So is it known which are the allowed Poisson tensors for the standard structure on the Hopf surface?
Oh, yeah, I guess I said this was unique. That's not completely true. It's like unique up to automorphism. And so, yeah, but this Poisson tensor is unique up to automorphism. Or, sorry, it's unique.
The Hopf surface as a complex manifold, and then you ask for all Poisson tensors such that this is subordinate to some generalized scalar structure. Is it known which are these Poisson tensors?
Yes, this is the only one.
This is the only one.
Like up to automorphism and scale.
So up to automorphism of the complex manifold.
Yeah.
This one and 0.
And 2, yes, and 0.
Okay. Mm-hmm. So this means that you are describing the full space of generalized scalar structures for the given complex structure.
Yes, exactly. Okay, so now I want to turn to discussing the solitons a little bit. So we discussed these last time. So what might we expect happens in this pluriclosed flow or generalized Kähler-Ricci flow or whatever, when the surface has no solution to rho b equals 0. And we just saw this is the general case, in fact, right? Most do not. So based on this sort of Perelman, this F functional monotonicity, this gradient flow for lambda that I discussed for generalized Ricci flow, maybe you expect it converges to a soliton. So here I rewrite this soliton equation, where now, of course, I'm implicitly assuming it's all coming from a pluriclosed structure. So some basic points are that if you have a pluriclosed soliton, then you can define this vector field, which is the gradient of F modified by, again, this Lie vector field is always there somehow rearing its head. This is actually holomorphic, and JV is killing. Okay, so this is a well-known feature of like Kähler-Ricci solitons generalized to this setting, okay, and modified by this Lie form. So in fact, for a generalized Kähler-Ricci soliton, you actually have two killing fields, in fact, right? So one coming from the I structure, one coming from the J. And so the isometry group it's either the isometry group has dimension 2 or these two vectors are aligned and you have a biholomorphic killing field. These are sort of the two options. So it turns out, sort of using this observation and a lot more, we can actually give a complete classification of solitons on surfaces, compact surfaces. Okay, and here's how it goes. So first of all, there's some work you have to do sort of using Kodaira classification and some add-ons by Telemann, you can show that the only possible complex surfaces admitting a soliton are Hopf surfaces. Or again, here now I write down kind of the more general definition of what a Hopf surface is. Okay, so the point is that the Z action upstairs can be a bit more complicated. So the alpha and beta do not have to align, and you can have this off-diagonal term. Okay. The case lambda equals 0 are called diagonal. And in fact, if we restrict ourselves to the GK world, you can show, basically this is due to Apostolov-Galtieri, that the only possible Hopf surfaces that can have GK surfaces are the diagonal ones. Because the point is you need a Poisson tensor which either which has a disconnected degeneracy locus. That's kind of the point. And on the non-diagonal Hopf surfaces, the degeneracy locus is always connected. Anyways, it's some technical point. But so the only possible candidates are diagonal Hopf surfaces. Okay, but more general than standard, right? So the standard ones are where the two moduli agree. Okay, and so a theorem from last year, joint with Apostolov and Yuri Ustinovsky, we give a complete classification of generalized Kähler-Ricci solitons, compact generalized Kähler-Ricci solitons in 4 dimensions. So precisely one of the following must hold. Again, the Kähler case is always there. So it's either Kähler, the metric is Calabi-Yau, Ricci flat, and I is plus or minus J. So that's one case. Or MGIJ is an odd type GK structure where this is, sorry, I didn't use this terminology before. This is the commuting case, what I call it, like the commuting case. And MI is a quotient of a diagonal Hopf surface by some cyclic group, so I'm stating it a bit more technically here. And the metric G and complex structure J are unique up to automorphism and scaling. So there's a unique soliton on these. Or it's part of an even type GK structure, where again, it's a quotient of a diagonal Hopf surface by some further cyclic group. And again, it's unique up to automorphism and scaling. And the part I didn't state is that actually these two metrics, the metrics are the same. It's the same metric. So like I said, this standard Hopf metric is GK in 2 ways, right? All of these solitons are also GK in 2 ways, right? So they're all GK with vanishing Poisson tensor and then with this log non-degenerate Poisson tensor. Yeah,
say
please.
again this even odd. Does this relate to these 2 killing fields where they commute or not?
Sorry, it has nothing to do with that. It's purely, so in dimension 4, the way I use the terminology is kind of special to dimension 4. It's odd type is just sigma 0, and even type is sigma is generically not 0. That's all.
It's only in, so, and in part 3, you have a non-trivial H flux.
And 2. It's non-trivial in both.
Oh, right.
Yeah.
But these 2 holomorphic vector fields, if you waste them, you get a relationship with the holomorphic Poisson tensor, or it's not. I think you mentioned when you were doing this, you were talking at.
Yeah, I forget the precise relationship. I don't think it's quite that because sorry, yeah, he was asking if the 2 holomorphic vector fields are related to the Poisson tensor. I think the problem is one of them is I holomorphic and one of them is J holomorphic. So I think it's not quite. I forget. I can tell you. But yeah, so in some sense, right, this is it's an extension of this Godeshan-Ivanov classification. First, we have to construct these solitons in the first place, and then show this uniqueness result. And in some sense, this is then an extension of sort of the Calabi-Yau theorem to complex, to generalized Kähler form manifolds.
So you know that there is this generalized Kähler structure on the Inoue surfaces.
Yes.
Well, those are not in the list of solitons. So
yeah, they do not admit solitons. Yeah, they don't admit them.
So then, what would you guess would be the outcome of?
I will say something about that in a bit. But basically, the point is you have to take a blowdown limit and it should collapse to a circle. In fact, this happens for homogeneous initial data, and is presumably the general behavior. But I can't prove.
Can this in way be the form to something? Because what happens here is like you have these non-diagonal Hopf surfaces, and the diagonal ones are like, the non-diagonal ones are like deformations of these ones. Yeah, I know.
So yeah, let me say a few words about the construction. So we construct them by maximal symmetry construction. So we impose this maximal T3 invariance. And then solve this relevant ODE. And I guess we discussed this a little bit yesterday. So I say it somewhere in here. So yeah, So in fact, these solitons, they split an isometric S1 factor where everything is invariant. And then these are exactly these Ricci solitons I discussed on S3. Okay, so it's exactly the same thing. And that does give maybe some possible clue, which I think got discussed yesterday about maybe how to classify these things on S3 is to really just prove that when you take a product with S1, it's complex or generalized K somehow. But I don't know how to do that. And then so the uniqueness, really the new we already kind of knew that these things existed, and the new contribution last year was the uniqueness. And this principally this comes from, of course, showing the maximal invariance in the first place, and then you can just invoke the ODE classification. To prove this, we construct basically an extension of this. So Aubin has this so-called I functional, which characterizes solutions of Monge-Ampere equation in the Kähler setting. So we give this sort of adaptation in a sense of the I functional to the GK setting. And then the key point is that it's actually like convex along constant velocity Poisson deformations. And you can use this to sort of prove that a critical point has to already be invariant, essentially. So this is how we get the maximal invariance out. Another remark is that they are global attractors for the flow starting with invariant data. So what I mean by that, right, is you start with a metric with T3 invariant initial data. It will it exists for all time, the solution, and it will converge to this soliton in the appropriate sense. And of course, it should be true for arbitrary initial data, but that's probably hard to prove. And then, yeah, I think the right way to think about this is as an extension of the Calabi-Yau theorem of generalized Kähler geometry. And so, I think an interesting feature of this is that it's not really, I think, correct or meaningful to make a distinction between sort of like Calabi-Yaus and solitons. I mean, like the rho b equals 0, like this standard Hopf metric is of course in this story on the standard Hopf surfaces. I mean, it satisfies all these things too. It's GK in two ways, and it's all a smooth family, right? So as you like move through the moduli of complex structures, the metric is it's all part of a smooth family. So really, like this family of solitons kind of is the correct moduli space of sort of non-Kähler Calabi-Yaus in this generalized Kähler setting. Okay.
And the Bismuth connections are all flat for all of them.
No. Because the uniqueness is very strong for that. The only one that's Bismuth flat is the standard Hopf surface, where the two moduli agree. Okay, yeah, sorry, I'm gonna maybe skip over a couple things. But yeah, maybe some questions. I wonder, is it a general feature of the story that they tend to be generalized Kähler in more than one way? I mean, I love that part of the construction. I have no idea if it's a general feature. Maybe that's something to do with T-duality. In fact, I guess after talking a bit with Jill earlier, I think it's almost certainly true that T-duality in this trivial S1 factor is taking class 2 to class 3.
That's precise.
Yeah. I think that's what's happening. We don't write that in the paper, but it must be true, I guess. Another general question I just think is interesting in this subject is maybe it's the case that every pluriclosed soliton in dimension 4 is actually generalized Kähler. I think this would be an amazing thing if it was true. And maybe there's some reason to believe it. I mean, it's yeah. And then there's this construction of Apostolov who sort of for any complex form manifold, you can construct this kind of second almost complex structure, which is compatible with it. And maybe somehow magically the soliton PDE tells you it's integrable. Some dream. I wonder also, but is it possible to construct solitons on this Calabi-Ekman S3 cross S3 where you perturb the flat structure? Also, I just maybe mentioned here again to sort of connect with this Podesta-Ferro thing from yesterday. We really still don't have a pluriclosed Bismuth-Ricci flat, non-flat manifold in higher dimensions. We don't know an example of this. So they constructed real, examples of just like real Bismuth-Ricci flat, but yeah.
About this, because I thought like all these Lie groups with the Bismuth connections, they all are flat.
No, well, I guess, sorry, yeah, I mean, I have to change the complex structure as well, right? So like on the Hopf surface, yeah, I have this flat structure and I sort of perturb it to produce solitons in a smooth family, right? I'm just wondering if something similar can be done on Calabi-Ekman.
Because the standard one on Lie groups.
Yeah, the standard one is there.
It's always flat, right? So
yeah.
It's a soliton for you as well, right?
Yeah.
Okay, so S3 cross S3 automatically has solitons. The question is,
can I produce like non-trivial ones? Yeah. Non-flat is what I mean by non-trivial. Yeah, non-flat.
Bismuth-Ricci flat, you mean with minusing Bismuth-Ricci?
So, sorry, yeah, I'm being sloppy. Rho b equals 0 or the derivative or something. Yeah. Okay, yeah, maybe, okay, I'm just gonna skip this part. Sorry about that. It ran away with me a little bit. Yeah, I just want to say a few words again, a bit more precisely about perhaps what this generalized Kähler-Calabi-Yau conjecture should be, some recent work. So the sort of initial theorem proved about Kähler-Ricci flow was a new proof of the Calabi-Yau theorem due to Sau. It goes like this. So if I fix a compact Kähler manifold with vanishing first Chern class, then this Kähler-Ricci flow exists globally and converges to the unique Kähler-Einstein metric in the Kähler class. It's like the most satisfying flow result you could prove. We have a complete description of what happens. And of course, it's a new proof of the Calabi-Yau theorem in particular, right? It's a priori giving the existence, okay? So it's natural to try to extend this to generalized Kähler geometry, but as we sort of already have seen, there's probably a lot of new features in play. But in one case, I think the conjecture should be, well, I think I know what the right conjecture is. So it's actually a very special case. So I fix a compact generalized Kähler manifold, and I'm going to ask that both of these GC structures are defined by global closed pure spinors. And again, like sort of pointing towards this, right? I mean, this is the case where I have this like global Ricci potential. And this really, if you think about it, is the most sort of direct generalization of the hypotheses here, right? So the two GC structures in the original Calabi-Yau theorem, both are defined by global closed pure spinors. I mean, the Kähler one, the Kähler form one always is, and then the C10 is equivalent to assuming the complex structure one is defined by a holomorphic volume form. So this is in some sense a direct generalization of the hypotheses here. Yeah, and then I think what should be true is that the solution to generalized Kähler-Ricci flow exists for all time and converges, and this is not a typo, to a Kähler-Calabi-Yau structure. So in particular, it'd be saying, if this was true, that there would be sort of no non-Kähler manifolds that are sort of this kind of Calabi-Yau type where the J1, J2 are both defined by global closed pure spinors. If this was true, it would have that implication.
But the thing is that,
Okay, so we're heading
Please.
towards that direction, right? Because like if you have metric Calabi-Yau, like you're saying, then H has to be 0, otherwise it's not compact, and it has to be.
the compactness.
Okay, so maybe the next thing I was about to say is already known then. Maybe we can talk about that. But I was going to say the Kähler rigidity is known. We can prove that. So yeah, so we can prove if you solve this generalized Kähler-Calabi-Yau equation and you have global closed pure spinors, then it's just Kähler-Ricci flat. Yeah. But okay, I'd love to know if that's already known. But yeah, we gave some proof of this. Yeah, so maybe I just skip this. So we can prove. Yeah, okay, yeah, I am running out of time. So we proved some results a few years ago in this non-degenerate case when sigma is invertible. This was joint work with Apostolov. So here I start with this non-degenerate generalized Kähler manifold, so sigma is invertible, and I do impose the hypothesis that the background is Kähler, not the metric, but just the background is a Kähler manifold. That's all I mean. Then we can prove the global existence, and we also prove some weak convergence, but let me leave that off. In some restricted settings, like the torus here, so on like a 4 torus, we can indeed prove the convergence. So the solution is global, and it converges to a flat hyperkähler structure. So again, this has, just like in this case, the Hopf surface, this has an implication for the space of generalized Kähler structures, right? It's saying that they're all deformable to a hyperkähler structure in this setting. Okay.
And it's not weak convergence. You fix you.
No, yeah, the weak convergence is in general, but again, because the torus is very special and you have some special background geometry to compare against, you can strengthen everything in a fairly elementary way. So yeah, so here you prove everything. And so in some recent unpublished yet work, we were sort of extending these things to the general case and in fact going a bit farther. So this is joint work with Apostolov, my postdoc Shin-Fu, and Yuri Yusunovsky. So I start with this GK manifold with this same setup. They're both defined by global closed pure spinors. And again, I have to ask for this Kähler background hypothesis, which of course is unsatisfying, but there it is. Then again, we prove the global existence. And then, so here we prove a stronger convergence statement. So if there exists a Calabi-Yau metric so I did not define what I mean here by GK, GIJ. But let's just put that in quotes and call that the generalized Kähler class. Then the flow, in fact, will converge to a Calabi-Yau structure. Okay. all I need for this, so the reason I put it in quotes is because I can be very naive about what I mean here, because all I need to know, it's basically just the connected component in the space of generalized scalar structures. I just need to know that there's a smooth one parameter family of generalized scalar structures connecting me from my given one to Calabi-Yau. So as long as I know that, then the flow will converge, okay, this thing. And that at least does have, it still has the same implication for the space of like generalized scalar metrics containing a Calabi-Yau metric, if you like. So for all we know, like on a K3 manifold, maybe the space of generalized scalar structures has infinitely many components or something like that. It's probably not true, but at least the ones containing Kähler metrics are like contractible, right? It tells you something about the topology of the ones that contain Kähler metrics. Yeah, okay.
Are there any examples where it's going to be disconnected? There's another one.
I don't think so. I bet they would know better than me. But yeah, because all these conjectures we point towards are suggesting, no, it's connected and contractible. That it sort of resembles the Kähler case where it's a topologically trivial space. And in fact, it probably has some convexity property even, but in some more delicate nonlinear way.
Of course, S3, the two spaces you're talking about, they were disconnected, right? The one in which plus and I minus commute, the other one.
Yeah, sorry. Yeah, of course. Yeah, I have to like fix this. I'm imagining a fixed Poisson tensor. Right. Yeah, sorry, of course. Already on that. Yeah, thank you. Well, but once you fix the Poisson tensor, I think then, yeah.
And is it always contractible? Even if there's only one.
I mean, that's the conjecture.
We have no
but
idea.
But the better answer is we have no idea. Yeah. Okay. Yeah, maybe I just sort of again emphasize something that came up earlier. So I think I believe in this conjecture, and then we have some, I think, reasonable evidence that it's true. But really, this global closed pure spinor case is very special. And already in dimension 4, you can see it's not capturing the most interesting new examples. Right? So you wouldn't capture anything new with this. But yeah, so we gave this classification in this earlier result with the Postloff-Usinovsky, but again, it has no conceptual underpinnings. I can't tell you, give me a complex manifold that satisfies XYZ really. I mean, without already using all this Kodaira classification and stuff. I can build you a soliton. It doesn't work like that. And again, yeah, all these sort of naive things you would guess, they're just not enough. So yeah, maybe there's some holomorphic obstructions, like a Futaki invariant. Maybe there's even a K-stability obstructions. Something like this might even be true. But yeah, okay, yeah, thanks for your attention.
Any questions or comments?
In your no-go result with Apostolov, this resonance, right? So,
Yeah, oops. Yeah.
I'm not sure. So the existence of the pure spinors implies that you have holomorphic volume form for both I and J, or it doesn't?
Well, not like directly. That follows after the fact, I guess.
Okay, so
but that's not how you prove it. But yeah, I mean, yeah. So the argument is, well, you can show that, that with these conditions around and both generalized complex structures defined by closed pure spinors, then the G is scalar and Ricci flat, and you basically are using this result of Godeshan. So he shows if you have C10 in Bott-Chern sense and the Chern scalar curvature is non-negative, then you have rigidity. It's 0. The Chern scalar is 0 and the metric is scalar. And this is basically how it goes. Like you can show that Bismuth-Ricci flat implies that this SC is non-negative.
I think there is an old physics proof of this, which, I mean, morally you're solving these linear spinor equations locally, and then you need to look at the trace of the generalized Ricci tensor and the generalized scalar curvature, subtract and integrate, then you get some positive quantity which gives the norm of H squared and the norm of the bilateral.
You can show me. Yeah. I'd like to see. Yeah.
So you said that you have these solitons on the Hopf surface. Okay, wait, sorry, 2 questions. So on the Hopf surface in your solitons, is it always the case that the 2 complex structures are isomorphic?
Well, not in the commuting type case, I guess, but in
the other case, let's say.
In the other case, maybe you remember So like for the standard structure on the hop, they don't agree, right? The one of the moduli is conjugated, right? I think it's alpha beta and alpha beta bar. That should be correct. Yeah, that's correct.
So do you know how you can?
Yeah, and that is also the case
freedom?
with the solitons. That's a general feature of that's just a general feature. That has nothing to do with the solitons. I think the only GK on non-standard diagonal hop have those moduli, like alpha beta and alpha beta bar. Yeah.
Okay, and other question is that, so you're saying that those solitons, we should think of them as being like Calabi-Yau metrics.
Yeah.
Not as extremal Kähler metrics, which are not Kähler-Einstein, but as actual like Calabi-Yau metrics. Or
I mean, I don't know, that word I think means n+1 things for any n, but I mean, for me, it's just, for me, I'm trying to sort of construct canonical geometries on non-Kähler manifolds.
Okay.
And you know, I want to guess what is a meaningful definition of canonical. And for me, this story of pluriclosed flow and generalized Ricci flow and the F functional and all this stuff naturally spits out the generalized Kähler Ricci soliton PDE. I mean, that's really what this F functional, I mean, right, so I want to take a Lagrangian point of view, right? I want to minimize an energy, in this case, lambda or F, this F functional from before. That point of view suggests the generalized Kähler Ricci soliton PDE. And that's what we classify.
So do you think that it's possible that maybe the problem, maybe the condition is not that you have a closed pure spinner, but just having a global pure spinner, just having two global pure spinners, but they're not closed? Because in the hop case,
but can you not? Oh no, yeah, I guess you can't always produce one. Yeah. Like if you know,
so one of them is a holomorphic condition, the other is a topological one, right? So the hop surface
Right,
there is
right.
no cohomology in degree 2, so you can always get a section of the canonical bundle.
the canonical bundles on the hop surface are trivial, right? Topologically, but not
the generalized ones. You mean.
no.
Or oh yeah, no, I know what you mean. Yeah,
And
exactly.
the generalized and the non-generalized. They're all
Yes,
trivial.
yeah,
topologically.
yeah.
But just going back to the holonomy question.
Yeah.
Because here, so somehow you're thinking of Calabi-Yau, like Kähler and Calabi-Yau. So these are two separate things that they intersect, and then somehow when you have Kähler, which is Einstein, it's Calabi-Yau.
Yeah.
Right. But once you start going towards like just losing up the Kähler condition, you impose SKT and you have the flow for SKT, but you could have just gone for holonomy UN.
You mean like classic? You're not on the,
like,
you're not on E.
This
You're just on
connection
like
is
T.
holonomy in UN plus the Einstein condition for the also the same curvature, right?
Yeah. Okay.
So you kind of drop the integrability of the complex structure.
I'm very hesitant to drop that,
Okay,
but
we'll talk
anyways,
about
yeah.
Any more questions, comments?
Yes, what do you think that these Inoue surfaces can they degenerate to?
Yeah.
So firstly, what do you know about existence of generalized Kähler Ricci soliton for Inoue?
They do not exist.
They do not.
That I have to use this Telemann result. So basically, Telemann shows that on Inoue surfaces that the total Chern scalar curvature can only be negative, but for a soliton, it's always positive. Everything for surfaces, that's true.
And so my question is, can you do something like for hop, where you have these non-diagonal hop surfaces, and then you can degenerate to diagonal?
Okay,
and then
yeah.
there at the limit is like
That,
this PAT
where
picture.
do I say that? Yeah, that's this like item 2. So, okay, yeah, I think what you say, I think is the hint for maybe why there's some K-stability obstruction. But okay, unfortunately for surfaces, right, as I think I mentioned, like for these non-diagonal hop surfaces, they don't have any GK at all. So it can't happen because you don't have any GK structures to begin with. But what almost certainly happens to the pluriclosed flow on those manifolds is it will converge to a generalized Kähler Ricci soliton on the degenerate limit, which is the diagonal hop surface, right? So the diagonal ones occur as the exceptional fiber in a family where every other fiber is the non-diagonal one. And so this is this complex structure jumping phenomenon that happens in Kähler Ricci flow. And I very much believe that that's what's happening if you start pluriclosed flow on non-diagonal hop. Yeah, just seems like the right thing to happen.
You mentioned the Calabi-Ekman manifold, some of the open problems. So have you looked already a little bit at that case?
No, I just it's kitchen sink. I can't stop myself asking these questions. So.
It has very interesting non-integrable complex structures.
Oh,
So
yeah.
also near, so some generalization of nearly Kähler, half-flex, left invariant structures.
Okay.
I mean, I understand that you cannot use at the moment non-integrable structures.
Right.
Perhaps it would be nice to have a flow which converges from non-integrable to integrable.
Well, yeah, I have some ancient by now work in that direction.
Ah, you have some.
But nothing at all concrete along the lines of what you're suggesting, but baby steps, I guess.
Okay, let's thank Jeff again.